So we are going to set up a spreadsheet that will automatically calculate allele frequencies for Hardy-Weinberg equilibrium. And the way this spreadsheet works is that we are able to put in random numbers and it will calculate the frequencies. And we can also manually input values here as well for P and Q. We have different options and it will plug those into the equation and also tell us whether the population is evolving or in equilibrium based on observations that we have for the next generation. So we are going to need to create this drop-down arrow and use some random numbers and basically set this up so that P and Q will always be calculated regardless of which number that you have or which value for P or Q that you have. You don't have to manually subtract one from the other. It will do that for you, which is handy. So let's get started with this blank sheet here. So the first thing that we will do is put in the rand formula. This generates a random number between 1 and 0. So it's a bit different from rand between, which will generate whole numbers. But the rand function is just fine for P and Q. But keep in mind that these two numbers are not related to each other. They're both completely random numbers. This Q is not the frequency that would correspond with this P value here. So just keep that in mind. So to create the drop-down arrow, we need to go to data, data validation, select list, and then we're going to select from these options in column C. And that allows us to choose different options. So we want frequency 1 to read whatever this option is telling us to choose. So in order to do that, we are going to use a VLOOKUP function. So we'll look up this cell and we want to read this table. We'll make sure that there are dollar signs there so that the formulas don't shift around as we're working throughout the spreadsheet. And we want the second column to be read, these numbers here. And we want an exact match. So we don't want anything to be rounded, just give the exact number as it is. So as you can see, it will input whatever we select. So this is basically the value for the P allele. We're telling it to choose a random value for P. It's giving us that. So we would need the spreadsheet to automatically calculate what the value for Q is. So keep in mind that both P and Q will add up to 1. These are both frequencies for alleles. P is for the dominant allele, Q, the recessive allele. They both have to add up to 100% or add up to 1. So you just subtract 1 minus whatever value that you have to determine what the other one is. But we'll have that set up automatically. So for this, we will just use 1 minus whatever value we have here. And for this frequency, it's going to equal cell C6 because this is the p-value. It's calculating the q value. Both have to add up to 1. If we know p, we know q. P is 0.36. That means q has to be 0.63. So those will match. And we will subtract 1 minus cell D3 to give us the other option. And we are doing it this way so that wherever we put P and Q, it will give us both values. So for frequency 1, we have P, but if we were using a random Q value, then frequency 1 is telling us Q, and frequency 2 is giving us the value for P. So we want those to be accurate. Based on whichever one that we use, it will automatically fill in the correct value for P and Q here. For this cell, we're going to use an ifs function. And basically, if functions allow us to test different criteria, and if some conditions are met, then Excel will give us a certain number or text. But the ifs function with an S allows us to have multiple conditions. So we need that because there are 4 different options, and we want whatever's placed into P to be the right value depending on which option that we select. So we'll start with ifs. This drop-down arrow, if what we select there says P rand is equal to P rand in quotations, then we want this cell here for P to read whatever is in the frequency 1 cell. But if this drop-down arrow says something else, like P manual, which we want it to say for cell P here, we still want it to use this value here, whatever's there. So if we have the drop-down arrow selected on Q rand, then it's going to be slightly different because if we have P selected, frequency 1 is telling us the value for P. But if Q is selected, frequency 1 is telling us Q, and frequency 2 would be P. So we want the right value to be entered in the right cell for P and Q. So if it says Q rand, then we want cell D3 to be read, basically. And same thing for Q manual. So we'll enter that in, and as you can see, it looked at the selection we have, P rand. It looked at the frequency we calculated for that and put that in the location for P. But if we add Q here, then it realizes that this value is the value for P, and this is the value for Q. So that's what we want it to do. And we'll pretty much do the same thing, but just make some minor adjustments here and just invert basically the C3 and D3 cells. So for Q, if P rand is selected, then we want D to be input because we want the value for Q And we'll adjust that one. And for the Q rand and Q manual, we'll put cell C3 there. So double check to make sure it worked correctly. So Q rand is 0.169. That should be in the Q spot. 0.83 is in the P spot. So far, so good. So now we can input these frequencies into this equation, the Hardy-Weinberg equilibrium equation, P squared plus 2PQ plus Q squared equals 1, or it all adds up to 100%, basically. So P squared is the frequency of homozygous dominant alleles. 2PQ is for recessive alleles, and Q squared is for homozygous recessive alleles. 2PQ heterozygous, P squared homozygous dominant, Q squared homozygous recessive. So we basically will just do what the formula says and take P, put dollar signs around it, because we're going to be using this again, and square it. Take 2 times P times Q and then Q squared. If we actually go out and observe the next generation of offspring that are born, we look at their genes, we see how many are actually heterozygous and homozygous dominant and all of that, and compare that with our expected allele frequencies. What is that going to tell us? Is the population in equilibrium or evolving? We will use our spreadsheet to help us assess that. So first off, I'm going to put a couple more formulas here. I have gray cells in the spreadsheet in areas where you would manually type in information, and other parts of the spreadsheet are going to calculate things automatically, but we would put in allele frequencies here based on the observations. This is information that we are given or that we collect, and we have to compare that with our Hardy-Weinberg values. So if this is what we actually observed in offspring born, what does that mean? So let's go to cell H13 and use a count if function, and it will count if the observed frequency matches the expected frequency. Basically, we're saying count if H12 is equal to H8. Then it will place a 1 in the cell, if not a 0. And we are going to copy that over and make sure that it worked properly. So like if this is 36%, it's the same, so it would show us a 1 if that were the case. But we had 40%, so it is not a match. And here we are going to use an if function and say if the sum of these 3 cells equals 3. So they all have to be matches in order for the population to be in equilibrium. That means that this population is in equilibrium, so we'll have it tell us that. But if any of the 3 have a 0 in it, then that means the population is not in equilibrium and it is evolving. if we look here, it's telling us that the population is evolving, which makes sense because this is what you would expect, and these frequencies are different. These alleles are shifting a bit for whatever reason. If we had, one of them is the same, but the other two aren't, it's still evolving because it's not an exact match across all three. Or, even two of them, they wouldn't even add up to 100% at that point, but just to show you that this formula is working correctly. But if we have, all three are a perfect match, then it is an equilibrium. And in real life, there might be a few percent or two that are within range, but generally that's what we are looking for. So that is basically it for this spreadsheet, and hopefully this was useful.